We have today with us for today's seminar Enrique Lopez-Rodriguez. Enrique did his PhD at the University of Florida, which is actually where we met for the first time, I think. And he, after his PhD, 7 years ago, he moved as an assistant professor of research to the University of Texas in San Antonio, where he moved to be a research fellow at also in Texas, but at the University of Texas at Austin, together with the McDonald Observatory. After that, he moved to even more western lands, to the sunny California, where he started working as a visiting scientist in the Statospheric Observatory for Infrared Astronomy, or SOFIA, where he was a rising star and quickly became a staff scientist. And he remained there for 3 years, winning a lot of SOFIA proposals in every cycle, a couple of them. And it was only until very recently, I think it was in March, no? This year.
2 weeks ago, yeah.
2 weeks ago, he moved as a research scientist to the KIPAC at Stanford University, very close in the Bay Area. So today, Enrique is going to talk about extragalactic magnetism using far-infrared astronomy, and you can start whenever you want, if you want to share the screen.
Yeah. All right. Well, oh, no, I don't want to leave. Let me think. Here. Okay. Can you see my screen? Oh. Can you see my screen?
Yes.
Oh, perfect. Okay. Well, thank you, Tanio, and thank you, the Institute, for inviting me today to talk about the latest results that are coming from SOFIA, specifically from our SOFIA Legacy program, which aims to estimate the magnetic fields in galaxies using a new technique, far-infrared polarimetry. Here you can see some of the results that I'm going to show today. So as he said, so I just started 2 weeks ago in Stanford, where I will be mainly focusing on working on this data. So let me start first with a video. And the video show the formation of galaxies. So here on the left, I show you the illustrious TNG simulation, where you can see the formation of stars, formation of galaxies. So every single data point represents a galaxy, and the brightest it is, the more stellar contribution is there. And then on the right, you see the density of gas. So you can see that in order to form cluster of galaxies, that you see that is like they start getting bigger and bigger and more massive due to gravitational collapse and dark matter energy, dark matter pressure. You also see the accumulation of dust and gas. So usually, historically, all the theoretical approaches and observational approaches are relating to gravitational dark matter and turbulence. But we also know that the universe is ionized, is moving, so there are ionized charges moving around, so there's some magnetic field there. So, and these simulations give you something pretty interesting and give you the magnitude of magnetic field as a function of time in the universe. And you see that at the beginning you have like almost, so in this panel now, you see the magnitude of magnetic field. You saw at the beginning that was close to 0, the very, very small. And then here on the panel on the right, you see the same video with the stellar contribution. You see the stellar contribution, you already see some massive star galaxies and some clusters, but you don't see much of the magnetic field there. But if you see the what's called the galaxies forming, you start seeing that the magnetic field is also amplifying and getting stronger and stronger. And you see that the peak of the magnetic field is happening more or less at the peak of the star formation in the history of the universe, more or less at C equal 2 to 3. And this happened because of supernova explosions, accretion onto supermassive black holes, and these outflows of the also with combination of star formation and the jets due to accretion onto supermassive black hole and make the magnetic field increase and magnetize the intergalactic medium. So you end up with a universe more or less at C equals 0 right now, where you have the contribution of gas, dust, kinetic energy, dark energy, and also you have a permeated full universe with a magnetic field all over the place, where you see the maximum of the magnetic field more or less in the center of the galaxies or the galaxy clusters, and you see a very faint magnetic field in the halo or intergalactic medium. Just to sum up, the two videos, the magnetic fields are amplified as a consequence of galaxy formation and turbulence driving dynamos. Basically, what happened is three different steps. At the beginning, you need to have a seed magnetic field, which is generated by one of these three mechanisms, the Birman battery, the Virgin instability, or plasma fluctuations. There are basically three fancy names just to say that the seed magnetic field of 10 to the minus 18 Gauss is generated due to collisions in the interstellar medium or fluctuations in the ionized plasma at the very early stage of the universe. After you have this very small magnetic field, the turbulence gas flows due to galaxy interaction, accretion flows, and supernova explosions. This magnetic field is amplified up to the 10 to the minus 5 Gauss. And then when you have a very ordered magnetic field, means the galaxy are when you have late type galaxies, for example, spiral galaxies or elliptical galaxies, you have the field has enough time to be ordered due to a differential rotation of the spiral galaxy, which we call a large scale dynamo. And the turbulence in this case is also driven by supernova explosions and magnetorotational instability in galaxies, which is the differential rotation of the galaxies. So these simulations give you the signature of this magnetic field. Here, what I show is the starlight on the left panel of two different galaxies. One of them is an early type galaxy, elliptical or irregular. And then at the bottom, you see a late type galaxy, for example, a spiral galaxy. In the middle panel, you see the direction of the velocity field. You see that the irregular galaxy or early type galaxy, you have a very anisotropic velocity field. Is no order yet, but you have the spiral galaxy. You see the velocity field is spiraling around the center of the galaxy, and this affects the magnetic field. So the dynamo is basically the conversion of kinetic energy into magnetic energy. So if you have a very ordered velocity field, you may end up with a very ordered magnetic field at the end. So you see here the direction of the magnetic field for early type galaxies are very regular. And when you look at the spiral galaxy, which has enough time to the dynamo to take place and amplify the field, you end up with a spiral magnetic field following more or less the spiral arms in the optical. So this is all simulations, but we live in an empirical universe. So let's go and take some measurements. Most of our knowledge right now is coming from decades of work using radio parametric observations. And here I will try to summarize in 3 minutes 4 decades of work. So One of the most spectacular observation that we have is this M51, the observation of the magnetic field in M51. Here, the color scale show the optical image of M51. You see the spiral arms with all star formation region peaking along the spirals, and the lines represent the orientation of the magnetic field. So you can see that the magnetic field follow the spiral shape of the galaxy. We know that you have the contribution of some order magnetic field, but you have some also turbulence within the arms, and you see that the magnetic field, the polarization due to the magnetic field peaks in the interarm, but not in the arm itself. When you look at the spiral galaxy Emission, you have this X-shaped structure as the typical feature for spiral galaxies that extend well below the galactic disk up to the halo. When you go and see the regular galaxy, you see something that I showed like the simulations before. You see a contribution of potentially maybe some spiral feature due to a slow rotation of the irregular galaxy, but you see a magnetic field that is very regular, maybe with some contributions that are radial and some contributions here, for example, these lines that are spiral due to the slow rotation of the galaxy. But you also have galaxies interacting. So in those cases, what you want to see is this magnetic field following the tidal effects of the interaction of the galaxies, and you see that the gas flow due to the merger make the magnetic field very turbulent, and the magnetic field are basically showing and basically following this tidal effect between the two galaxies here. So these observations and simulations open new questions here. So how did the evolution of galaxies in merger affect magnetic fields? Is the single galactic magnetized, and how it get magnetized? How has the magnetic field been amplified by the interaction and or star formation in galaxies? And what is the structure of the magnetic field around active nuclei? So even though we have simulation and some observation of radio polarimetry, we still have some open questions here that we'll try to answer with the new observation that we have. In order to do that, what we are doing here is following a multi-wavelength observation approach. However, not all wavelengths are good enough. In order, well, not all wavelength trace the magnetic field. For example, in this case, I already showed you that the radio trace the magnetic field due to synchrotron emission. Basically, what you have is relativistic. You have relativistic electrons orbiting around the magnetic field in the galaxy. So then, kind of like illuminates illuminates the magnetic field in the galaxy. But back in the 80s and also in the 50s and 60s, there was a lot of effort to estimate, to try to trace the magnetic field using optical observations. Here I show the same galaxy, M51, in the optical, oops, sorry. And again, so the contours show the total intensity in the optical, which is the contribution of the stars, and the lines represent the polarization angle. However, here what you see is this azimuthal or centrosymmetric pattern around the core, and this is the specific signature of scattering polarization. What you have is light from the center moving away from the core, and the position angle of polarization is perpendicular to the last direction of flight. So let's say that you have electron moving from the center away in the outer parts. So then scattering to our LIO side. So the polarization angle will create this azimuthal pattern, which is the characteristic of the scattering. And also the degree of polarization is very high, which is characteristic of the Dyson electron scattering. Pavel and Clements tried to estimate the magnetic field or measure the magnetic field in the infrared. And this is what they did here. So in this case, the color scale show the degree of polarization, how much of the light is polarized. If you expect that the polarization is coming from magnetically aligned dust grains, in the near infrared, you should expect some few percent of polarization, but you can see that the polarization here go from more or less to 0 to 0.1%. And this is the tail of the scattering along a wavelength. So basically all in the optic, most of the observations in the optical and all of the observations and most of the observations in the near infrared does not trace the magnetic field at all because they are mainly dominated by that scattering polarization. Another example is M82. So here M82 is a Starburst Galaxy. You see the remnant of the spiral galaxy in the center on the right. And then you see these big galaxy outflows due to very strong star formation and supernova explosions in the center. Back in the 90s, they tried to estimate the magnetic field in these outflows using optical, but again, you still see this azimuthal polarization pattern along the outflow, which is the signature of scattering. And you don't see much polarization in the disk because it's extinguished by dust in the spiral galaxy. So it's no information about the magnetic field at all. In the 2000s, Terry Jones did infrared polarimetry of the same galaxy of M82, and he observed basically the same thing. So you see this centrosymmetric pattern too around the galaxy, but you start seeing some hint of something that is no scattering here. So what he did was a mathematical subtraction of this centrosymmetric pattern. It's basically just subtract a circle around the core and see what the residual looks like. And this is what the residuals look. So here you don't see the scattering pattern anymore, but you see something interesting. You see some of the polarization angle following the disk and some of the polarization angle perpendicular to the disk. And in the infrared, what you're tracing is the absorption of starlight due to magnetically aligned dust grains. I will explain a little bit how the mechanism happen, but the position angle in the infrared will tell you the orientation of the magnetic field along the LIO side that you are looking. So here the magnetic field looks like to be parallel to the disk, and in the center it looks like to be perpendicular to the galactic disk. So you have some kind of like magnetic field along the outflow, and you have some magnetic field remnant from the spiral galaxy in the galactic disk. In radio, that we see that where we know most of our knowledge comes from radio. Here, the picture of M82 is a little bit more complicated because M82 is also interacting with M81. So here, what you see is a peak of polarization in one side of the of M82 with some perhaps some tidal effect here, and you see some hint of the galactic outflow here in this area in the north and maybe in the center, but it's very complicated to get any information in the center here. So if we want to know what happened with the magnetic fields, you see that these three wavelength ranges doesn't really give you much information about the magnetic field along the outflow itself. So what do we do here? Is one specific polarization mechanism that we haven't told here yet, and is thermal polarized emission due to magnetically aligned dust grains. So what you have here is a sketch of how dust grains are aligned along the magnetic field. So let's imagine that you have an interstellar cloud in one of these spiral galaxies in the spiral arm. So the cloud has dust grains that are co-spatial with a molecular dust. Then this cloud is illuminated by some background object. The dust grains absorb the light from this background object and start rotating, and then create magnetic momentum processing around the magnetic field, and then the dust grains, which are not spherical, end up with the long axis of the long axis of the dust grain perpendicularly aligned to the direction of the local magnetic field. So if you look the light in extinction, that means that the light in the optical and near infrared, you only see the light that has not been absorbed by the dust grains. You see the polarization angle are more or less parallel to the magnetic field line. But those dust grains also emit in the far infrared at around 20 to 100 Kelvin. So these dust grains are at the temperature of 20 to 100 Kelvin, which emits in the far infrared at 50 microns up to 1 millimeter. So then what you have is the long axis of the dust grains emitting. So then you have the polarized light, the polarization angle will be perpendicular to the magnetic field line. So in this case, if you observe in the far infrared on 2 millimeter and you see polarization, the polarization angle is always going to be 90 degrees away from the magnetic field line. So mathematically, you can just subtract 90 degrees or add 90 degrees, and you end up with the average orientation of the magnetic field in the plane of the sky. So just as a sum up, this is the mechanism that I show here as a function of the wavelength. Here is just a sketch of it. So the electron that's scattering, you see that dominates in the optical and the near infrared. And if you try to estimate the signature of magnetic field due to the correct absorption, that I call here absorption polarization or emissive polarization, you need to have a 1 order of magnitude lower. So which is what Terry Jones is trying to do here. Or the other option is going to longer wavelength. If you go to the mid infrared, the absorptive and emissive polarization are more or less comparable. And you may be able to observe some magnetic fields, but the issue is like both of them are orthogonal to each other, so it may cancel out in some areas. And the way to go is to go to longer wavelength, where you have the peak of dust grain emission at around 100 microns, and you are mainly dominated by thermal emission of magnetic aligned dust grains. And here you have the contribution of synchrotron. When you go to radio, it dominates and you don't have much contribution of thermal emission. So you want to estimate magnetic fields in galaxies, which we know that peaks more or less at 100 microns. That's going emission peaks at 100 microns. The far infrared is your friends in order to estimate the magnetic fields. Let me continue with some definition before I go and enter into the details of the observations. I'm going to be talking a lot about these large scale fields and small scale fields. That all depends on the correlation length of the turbulence. The turbulence in galaxies are driving from supernova explosions that usually has a typical length of 50 to 100 parsec. So any single magnetic field that are smaller than this turbulence scale, we call small scales, and those of them that are measured with larger than 50 to 100 parsec, we call it large scale fields. But from the observational point of view, we also distinguish the magnetic field based on the average within the element of resolution of our instrumentation. So we call it regular coherent magnetic field to a magnetic field that is very well-defined direction within the beam of observation. So here I show in red, for example, the beam of our observation, and the magnetic field is all in the same direction within the beam. So we call it regular. But this is not the norm. So the magnetic field within the beam it has many reversals. So we call this one a turbulent field. And here you have two different fields. You have one that is isotropic, you have many reversals, and the average for all these directions of the magnetic fields tends to go to zero. But you have several reversals, and you average out all these directions, and give you an average orientation. For example, in this case, 45 degrees more or less. So you call an isotropic turbulent field. So what do we measure with far infrared and what do we measure with radio? So here with synchrotron emission in radio, if you look at the total intensity traces the total magnetic field in the plane of the sky, and it gives you the information about the strength of the magnetic field. So this total intensity synchrotron emission is sensitive to the column density of the electrons, of the cosmic ray electrons, and also to the magnetic field strength. All these polarization synchrotron emission study the polarized light, and they trace the order magnetic field in the plane of the sky. This order magnetic field is the contribution of two different fields that I already mentioned before. One is the regular field, which is constant in the beam size or the angular resolution of the telescope, and then isotropic turbulent field. So you can imagine that the regular field is always constant. You don't have reversal within the beam. So the polarization of polarized flux will be constant if you have a regular field. But if you have some decrease of the polarization in radio, it may be due to a decrease of the average anisotropic turbulent field in the beam. So this polarized synchrotron emission depends on the B field strength and geometry of cosmic ray electron density. In our case, we are interested in the thermal emission. So how that compare? So for the total thermal emission, it traces the dust grain emission, but it doesn't really tell you anything about the magnetic field. It's only sensitive to the dust grain size and composition of the dust grain. The polarized light instead is giving you the orientation of the magnetic field if it's through thermal emission by rotating the position angle by 90 degrees, because we know that the dust grains are the long axis of the dust grains are aligned perpendicular to the direction of the magnetic field. So you have to rotate those position angle, and it's tracing the order magnetic field in the plane of the sky. So in this case, the degree of polarization and polarized intensity are not sensitive to the strength of the magnetic field, but they're sensitive to the geometry of the magnetic field along the line of sight. They're also sensitive to the level of alignment of the dust grains. Not all dust grains are aligned. And also you have also is sensitive to the size and the composition and the column density and temperature of the dust grains. So the other thing that we need to take into account is that we are tracing different structures in the galaxy. So here what I show is the same galaxy. So NGC A91 is a H-on spiral galaxy. So here I show the image in radio at around like 6 centimeters, I think. And then you see new observations with Hawk, the far infrared, at 154 microns. You can see that the scale length, so the height of the galaxy that trace the far infrared, the radio, sorry, is higher than the one that trace the far infrared. You are looking, the far infrared, you're looking deeper into the galaxy, and you are not affected by any emission in the halo as you have it in the radio. So you have to think that every single time that we observe something in radio, the polarization that we see is coming from the contribution of the whole column density along the line of sight onto the object that you want to observe. So you're observing in the direction face on. So you are integrating through the halo and then integrating inside of the disk. So the whatever polarization that you are seeing is the contribution of all that line of sight. While in the far infrared, you are the halo doesn't emit in the far infrared. You only see the contribution from the mid plane of the galaxy here. So for example, here the polarization in the far infrared is very well aligned with the disk of the galaxy. And in this case, you see this typical X shape in the far infrared going into the halo because you have the contribution, you have several contributions along the line of sight. So now that we are all experts in polarimetry and radio and far infrared, and we know what to expect, So this is the key science projects, the key science topics of our program. So what we are trying to do here is to construct a first comprehensive empirical picture of magnetic fields in a multi-phase ISM with a set of galaxies in order to estimate how the magnetic field looks like when you have a spiral galaxy with, for example, active galactic nuclei in the center. What happened with the magnetic field when you have a strong star formation. We also want to provide constraints in the sense of like how the magnetic field looks like at different phases of the interstellar medium on different parts of the galaxy for galaxy dynamo theory and for simulations. We also want to know what happened to the disk of the galaxies after the interaction of galaxies, and we want to provide also constraints on energetic particles. So we know that it's a high contribution of astrophysical neutrinos coming from starburst galaxies, and those neutrinos models, the models to explain that one, the contribution, the production of neutrinos are depending on the magnetic field strength, geometry, and current density. So this is something that we can provide to them. So in order to do this project, we observe, we use the Statospheric Observatory for Infrared Astronomy, so or SOFIA. SOFIA is a 2.7 telescope in the back of a Boeing 747. Is meant to work from the UV to the far infrared, but is optimized to observe in the far infrared. So right now, most of the instruments that I show here, so 7 instruments plus the newest one is HAWK, which is the imaging polarimetry, working in the 50 to 200 microns. They usually work between the 5 to 300 microns wavelength range. So the airplane fly at around 30,000 to 45,000 feet. This is, I think, like 13 to 15 kilometers over the sea level. And usually we have like 10 to 15 people on board. So the Boeing 747 usually have 300 people inside. So, but we only have 3 pilots, 2 to 6 mission crew, which include the instrument operator, telescope operator, and safety people, and then 1 to 3 scientists, and sometimes we invite high school teachers in the US to fly with us, so they can come back to their schools as heroes or astronauts almost, and show the students how NASA do science in a Boeing 747. And we fly around 8 to 10 hours overnight within the weekdays. So specifically, we show HAWK, which stands for the High Resolution Airborne Wideband Camera and Polarimeter, or PLUS, depending who you want to say the plus for polarimetry or just the plus. It works, it's imaging and polarimetry working from 50 to 200 microns, has an angular resolution of more or less up to 5 arc-second to 20 arc-seconds, and observe the total and polarized emission from dust grains these 5 different bands. So we are able to trace dust temperatures in the range of 10 to more or less 100 Kelvin, where for galaxies, this is perfect because the host galaxies peak more or less around this range. You want to know more about the instrumentation, I'll be happy to talk later on, but this is a sketch of the instrument. So for our project, we have a sample of 18 galaxies. They're all a mix of different type of galaxies. The reason is because we are flux limited by the sensitivity of the instrument. So we have some interacting galaxies, some AGNs, some starbursts, a lot of spiral galaxies in order to provide constraints for galaxy dynamo theory. But here, what I want to say is like it's a lot of data that exists and it's already in the archive and it's all public. And this is the point of this program. So we are requesting around 160 hours of observation on top of what is already available on the archive. So you can go to the SOFIA archive of our website, And this data is available and is ready to go. When you go to the SOFIA archive, you have raw data and science-ready data products, and it's all ready to go. And you can do your own science, and you don't have to wait for us to reduce the data for you, because the program already gives you data. So this legacy program, every single data that we have is public right away. So you don't have to wait for us to produce products. But what we do is to produce high-level data products, for example, estimations of the stock parameters, or also estimations of analysis of the polarization from specific objects. So this won't be possible without a very fantastic legacy team here. So you have two of them in this meeting. So you have Tanio and Costas too, but mainly the legacy team is a combination of an international group of people who knows a lot about instrumentation magnetism, infrared and radio polarimeter. We have imaging modelers, theorists, and also instrumentation, because we need to know a lot about the polarization instrument in SOFIA, and also we want to know about Herschel too. So all the legacy team has two PIs, myself here in the US, and Suyan Mao in the Max Planck Institute, who is the expert on radio polarimetric observations of galaxies. So now that we know about all the legacy team, let's see what kind of data that we get. So the first one that we got last year was the spiral magnetic field in 1068. So NGC 1068 is a grand design spiral galaxy. So you see here the color image is the optical image of the galaxy. You have in the center Astrophysics nuclei, which basically matter accreting onto a supermassive black hole and ejecting a jet here, very, very bright in the X-ray. And you have a spiral galaxy around the hosting this AGN. What we observed here was that the magnetic fields due to magnetic aligned dust grains tightly follow the spiral arms, the optical spiral arms of the galaxy. Let's look at the data, and this is what we see here. So in this panel on the left, I show the lines are the observations. It show the magnetic field orientation. So what we did was to see what is the behavior of the orientation as a function of the azimuthal angle. So what happened counterclockwise so around the center of the galaxy. And what we see is that the degree of polarization change as a function of the azimuthal angle, and also the position angle of polarization change as a function of the azimuthal angle. For example, these 220 degrees correspond to, so 0 is north, so you move around, and 220 correspond to more or less this direction. So you see that is almost radial, and you see these vectors more or less going radial. And if you go to 0, you see that these angles are more or less azimuthal, and you see those more or less azimuthal. So this variation is coming from two different effects. One is the inclination of the galaxy, and the other one is that the magnetic field orientation is not pure azimuthal. You have some pitch angle. And what we observe here is that you can explain the variation of the degree of polarization and position angle polarization using a very simplistic two-dimensional logarithmic spiral. So the host galaxy has order 3 kiloparsec scale spiral magnetic field following the optical spiral arms, more or less the optical spiral arms of the galaxy. The most interesting things are happening when you go to the center of the galaxy. So here, what you see is like the H alpha emission, where it tells you the star formation regions. You see a peak of star formation in the south west of the galaxy, and you don't see much polarization. And this is because the star formation is distorting the magnetic field at small scales, so which produce average null zero polarization in the beam side. And when you go to the center, you have the contribution of the AGM, which is highly, so it's a low polarized. So in this case, what you have is a 0% polarization. So if we go to object that's a little bit more complicated, you have M51. So this is a spiral galaxy, as you can see in the center. Again, so the color scale is the optical, but you have a companion here. So the polarization, the magnetic field may be affected by the companion galaxy. And this is what we are seeing here between the radio on the right and the far infrared on the left. So the streamlines that you see here is artistic presentation of the magnetic field orientation. And you see that the radio is very ordered at large scales following the spiral arms. But when you go to the far infrared, you see that that also happens in the inner part. But when you go to the outer part, the magnetic field became a little bit more unstable, more distorted. And this is something that I show here. So, on the left, I show the total intensity of the far infrared and the 3 and 6 centimeter, and the lines represent the magnetic field orientation. Here, what I show is on the right, you see the magnetic pitch angle as a function of the radius. So this line represents the core. So the line, the dash line, the vertical dash line represent the core, and the outer part represent the outer part of the galaxy here. So you see that the pitch angle in radio, so the magnetic field structure in radio and far infrared, if you study the whole galaxy as a whole, doesn't change. But you need to start separating things. You need to separate what happened within the arms and what happened in the arms. And this is where things get more interesting. And you see that when you have diffuse emission as the dominant contribution of matter, you see that the magnetic field structure on the radio and far infrared are similar. But when you go to the spiral arms, they start separating to each other. So this happened in the outer part of the galaxy, mostly in the north part here and in the south part here. We think that this is due to the potential interaction with a companion, or with the strong star formation in the spiral arms that you see here in the north. In order to look a little bit more in detail, so what we did was to look at different tracers. So what happened with the neutral gas and what happened with the molecular gas too. So here I show in the second panel, I show the molecular gas that follow very tightly the spiral arms of M51, and you have the neutral gas at the bottom. And you do the same game as before. You show the pitch angle as a function of the radius. You see that the total intensity in far infrared and radio follow the same structure. So the spiral arms in total intensity, wherever there are stars and diffuse gas, they follow the same structure. But when you go to the CO with the molecular gas, the pitch angle is lower. And when you go to the neutral gas, the pitch angle is even lower. So here, if we focus on the CO, so you have this pitch angle here is this crosses. So that means the pitch angle means that the H1, the arm is slightly tighter, so in the inner side, and the magnetic field is slightly larger. So that means it's in the outer part of the CO. And then when you compare with the magnetic field, these get a little bit more complicated, because you have the magnetic field change as a function of the radius, and both the morphological spiral arm and the magnetic arm crosses around in the outer part of the galaxy. So again, we think that all these interaction, all this behavior happen because of the star formation region and or the interaction with the companion galaxy. So just to finish after this one, so after this galaxy, we observe a little bit more complicated galaxy. This is a Centaurus A. So this galaxy is thought to be the remnant of a merger with the combination of a elliptical galaxy and a spiral galaxy. So in this case, what you have here is the remnant of the spiral galaxy in the center, which is all distorted and warped, and the elliptical galaxy in the halo, and you have a very powerful active galactic nuclei in the center, ejecting these very mass and very extensive, powerful jets into the galactic medium. This is shown in this video by Killing, where you have the elliptical galaxy, the dust lane, and you have this warp magnetic field in the center, this warp disk in the center. That what she did here is to combine all the velocity field, the velocity distributions, in order to explain this structure here in the infrared as a disk that is warped due to the interaction of the galaxy. In this case, what we introduce new in the picture is the magnetic field in this warp disk. Here what I show is the 89 microns images of Centaurus A observed with Hawk. The contours represent the total intensity, and you see that the contours are warped, and you see the center is very bright because you had the contribution of dust heated by the active galactic nuclei, and the lines represent the orientation of the magnetic field, and you see the magnetic field tightly follows the warp magnetic field, the warp molecular disk, and then you have a very distorted magnetic field around the AGN, potentially due to some AGN activity in the past. What I did at the beginning was to try to explain that behavior, that measurements of magnetic field using a large scale regular symmetric field. Basically, what I did was to assume a 3D spiral magnetic field where you have a pitch angle in the galactic plane, what I show here, but also you have some vertical magnetic field along the jet, which is characterized by the helical B field with two parameters: the pitch angle along the jet, and also the vertical scale, how big the jet is. And you need to project that onto the plane of the sky. And this is the best fit model to the observations. As you can see that the large scale magnetic field is more or less in the same direction as this lane of that lane of the galaxy, and the magnetic field also can explain the formation of the jet, which is the jet in this direction. When you compare with the optical observations, they all seems to be agree. So you actually see that the magnetic field orientation in the optical is very well ordered, of around 3 kiloparsec scale, and you see also that in my model, but things get more complicated in the far infrared. So here, what I show now is the black lines show the model that I showed before. So this is the model coming from a fitting routine of the 5 parameters, which is the pitch angles and the vertical scale, the inclination, and the tilt angle, to the data. And the data are the blue lines. And you see that even though the absolute difference between the model and the observations are 3 degrees, is a huge dispersion here of 22 degrees, 20 or 23 degrees. And this dispersion is not due to the intrinsic uncertainty associated to each polarization measurement, because it's very high signal to noise. I maybe something different. So that means that the largest scale regular field cannot fully explain the average B field orientation in the far infrared, but it can explain the B field in the optical. So our interpretation here is like the largest scale B field in the optical may represent the remnant of the B field, but we need another contribution in the far infrared. And we did something here. I think it's a little bit new in the extragalactic magnetism. So what I did here is to compute the polarized intensity versus the total intensity, and you see here that and every single point is the polarization measurement. So every single vector here represents every single dot here, and you see three different blocks of data. So one of them is this one here on the left, so very low intensity, and then you see the degree of the polarized intensity increase, and then you have a dramatic drop, and then you come back, go increase again at higher intensity, and then you have a wall of degree of polarization that doesn't um, you have a wall here of intensity, and you have some very sparse data points in the outer part. So if you plot these three different groups as a function of as a cut with the total intensity, you end up with these three different groups. So the black one represents the outer disk, which is like very highly polarized, up to 15%, and low intensity, low column density. And you have the medium one, which is the medium intensity regime, which is the molecular disk, and very tightly follow the warp disk. And then you have the large intensity, which represent the star formation regions and the AGN itself. So when you plot these three regions as a function of the temperature, what I show here on the bottom, the temperature, the column density, and the velocity dispersion of the molecular gas, which is a proxy of the kinetic energy of the gas. You see that every single region or region has a different behavior. So the black represent the outer disk, is very highly polarized in all of them. And then when you go to the molecular disk, you have a decrease of polarization. And you also have a decrease of temperature, and you also have a decrease of column density, and you have an increase of column density, of velocity dispersion of the molecular gas. So our interpretation is that the deeper you go into the molecular disk, the more anisotropic is the field. So that means that you have more turbulence, the kinetic energy increase. So, and you have a higher contribution of small turbulent fields in the polarization measurements. So in the outer disk, you may be dominated by the large scale molecular, large scale regular field. But when you go deeper into the warp disk, because it's very messy, basically, and you have a lot of turbulence, you have a high rotation, this high rotation, this with the high rotation, you end up with the increase of the small scale turbulent fields will contribute into the magnetic field and contribute into the dispersion that we observe in the far infrared. So the conclusion here is like galaxy interaction is enhancing this turbulent B field at small scales, which may be a reason of increasing the magnetic fields in galaxies at the early stage of the universe. Just to finish with the galaxy that I showed before is the M82. This is a Starburst Galaxy that, as I mentioned before. So here what you have is the remnant of a spiral galaxy with a strong star formation in the center that's producing this large galactic outflow that is pushing away a lot of matter. So you see, for example, the concentration of dust in the intergalactic medium due to the expelling of matter of galaxy supernova exploding in the center. As I mentioned before, the three wavelengths, optical, infrared, and radio, didn't show much of the outflow, but the far infrared observations are highly dominated by the magnetic field in the outflow of M82. So here the lines represent the magnetic field orientation, and you see that all of them, most of them are perpendicular to the galactic plane or parallel to the galactic outflow. So here then we have several questions. So what happened with this galactic, with this magnetic field? This only in the center or extend up to the intergalactic median? And what is driving this magnetic field in the, what's the drive of this magnetic field in the center? And also what happened with this magnetic field? Do they go into the galactic median or they come back and feedback the galaxy? So in order to do that, what we did was to do a combination of so what we did was to modify this typical Davis-Janow Fermi method that um, is a method that gives you the contribution of the magnetic field strength on the plane of the sky by adding the contribution of the large scale flow. The large scale flow is because you have a galactic wind that's pushing all the matter away, and it may be stretching the magnetic field along the galactic outflows. So you need to estimate the contribution of it. Also, something that we did new here is to combine the extragalactic knowledge with the knowledge that the solar physicists have done in the past few decades. They are the experts on MHD. The sun has been more studied forever in terms of galactic dynamos, and you see here the interpretation of the magnetic field lines going from the corona or from the surface of the sun, and some of the lines go into the interplanetary medium, which they call open magnetic field lines, and some of them look back again to the surface of the sun, and they call it as closed B lines. So we wanted to use their same methodology, which is a potential field extrapolation, in order to see what happened with the magnetic field lines in MET2. And this is what I show here. Basically, what we did was to solve the Laplace equation, which has two different conditions. One is using all the measurements of the galactic field in the of the magnetic field in the plane of the galaxy, and assume that the magnetic field lines are zero in infinity. And these lines represent the integrated with extrapolated magnetic field lines from the center of the galaxy all to the way to the intergalactic medium. So if the magnetic field would have been not strong enough, these magnetic field lines may be going down again into the galactic plane, but we figured out that the energies between the kinetic energy and the magnetic field energy are more or less in equipartition, which is what I show here in these radial profiles. Is the radial profile of the kinetic energy in black, and the radial profile of the magnetic energy from the large scale magnetic field along the outflow, and some magnetic field that we found as a residual in form of bow shocks propagating along the intergalactic medium. And we see that the energy of these two contributions along the galactic outflow are in equipartition with the kinetic energy. So we end up with the situation that the material escapes into the synchronuclear galactic medium, driven away by the kinetic energy of the outflow with the galactic outflow, and the magnetic field doesn't come back again into the galaxy because the magnetic field energy is not higher than the kinetic energy of the outflow. So just to finish with the open questions, now we can provide some answers. In this case is how did the evolution of galaxies merger affect magnetic fields? We know that galaxy interaction amplify the magnetic field at small scales. And then we know that the synchronous galactic medium can be magnetized due to the galactic winds, because the kinetic energy is larger than the magnetic, was in equipartition than with the magnetic energy. And then we know with the study of M51 that the star formation and interaction with other galaxies can modify the magnetic field. And surprisingly, with these two galaxies, with Circinus 1068, we have been measuring that the magnetic field in the host galaxy of these AGNs are very ordered, actually, and you can explain it with a very simplistic large scale order field with a typical pitch angles of 15 degrees. So, and now it's like stay tuned for more results. The Centaurus is gonna come out tomorrow, so stay tuned with that. And because it's more results coming soon in the next couple of years too with this Sophia Legacy program. So if you have any questions, I would be very happy to take it.
Thank you very much, Enrique. And yes, as you say, now it's the opportunity for the people attending to ask questions. Please raise your hands or just ask directly if there are not many. I've seen one hand raising, Nikos.
First of all, thank you very much. Very, very interesting work. At least for me, it is really interesting and really good work. So I want to ask you about the basics. So if you could go back to slide 15.
Yeah, let me share back again. Share slide 15. This one?
Yes. So for example, in the case where people remove the scattering, bottom left.
Yes.
Can we be sure that this, whatever we see, is dichroic emission and not absorption, for example? Because different parts of galaxies may have a different temperature and emit in different. So for what I'm saying is maybe this is a tracer of emission in one case and absorption in another, which are indeed perpendicular to each other, no?
Yes, exactly. Yes. Yeah. So if I understand correctly, what Terry did was a pure mathematical subtraction of the position angles. You can see here in the previous slide, this is what the data looks like. As you can see, is mainly dominated by scattering. As you know, scattering is highly polarized. So you can have here polarization of like 5, 6, 10% of polarization. And he was trying to get the signature of something that is very low polarized in H band, maybe up to 1% or lower. So basically what we did was mathematically subtracting azimuthal polarization pattern and then see what the residuals look like. He didn't do any extrapolation of the behavior of the degree polarization as a function of wavelength because he only had the H band, even though you can use the R band in this case. So I think that there is a lot of uncertainty, at least in the center, where maybe a contribution of very hot dust in the H band, maybe you have 800 Kelvin hot dust here that give you dichroic emission or extinction. So you may have here a high contamination. In the host galaxy, I think it's mainly extinction. So we may be like pretty sure that this is like dichroic absorption by magnetic dust grains heated by starlight. But in the center, you may have the contribution of both for sure. But it's very complicated to do that. So actually, now with our observations here that I show, maybe we'll be able to compare or estimate how much of the emission coming and how much of the absorption is coming from the H band. We haven't done that, but that will be a very interesting thing to do.
Thank you. And I have actually a lot of questions, but if you could go also to okay, I'll just if you could go just to slide 20. No, 17. Sorry, 17.
No problem. Yeah.
Yes. So for scattering. Do we expect the same behavior for any type of scattering, for example, Rayleigh or Thomson?
No. I put here one example just to show the cartoon way of the grid, but no. So like the scattering has, if you have dust scattering, electron scattering, or Rayleigh or Thomson, you have a different behavior of the wavelength. The polarization as function of wavelength are slightly different, but all of them, you have a decrease of the relative contribution of the polarization as a function of wavelength. So in order to have high contribution of the, for example, dust scattering longer wavelength, you need to have a large dust grains comparable to the incident wavelength. So in case of these galaxies, you need to have dust grains up to 20 or 100 microns, which have not been seen before, in order to have a contribution of the dust scattering. And then you have the contribution of the behavior of lambda to the -1 or lambda to the -4, depending on the scattering behavior, for sure.
Thank you. And if I may, one final question, and then I'll let other people talk as well. Could you make a comment on what would you expect, or if you have already observations on barred galaxies? So how would the polarization look like in bars?
Yes, so the closest one that we have right now is, we have two of them. So let me go to the first one. So density has a inner bar in the center, very small one. And you see that the, let me go just to the big picture here. And you see that the polarization in the center is parallel to the inner bar, which is more or less 45 degrees. And then after that, you have this twist in the outer part and the small and the lower part, and then follow the how's called the spiral arms. And then you have 1097 too, which is a bar galaxy, but we only have the for now we only have the observations in the inner 1 kiloparsec, which is dominated by the circumnuclear star formation region. But in radio, they have the whole galaxy for 1097. So it is one here on the top. And they actually see one of the strongest magnetic field in a galaxy in the inner bar. So you have the compression, you have the compression, so the inner bar compress the magnetic field and make it to be stronger. And also in the edges of the magnetic field of the inner bar, where the inner bar became the spiral arms, you see a low degree of polarization in this area. And you see that the magnetic field is along the bar, and in the center, the spiral down into the central AGN, as you can see here in the black lines, is the radio polarization data. And you see that at large scales is more or less 45 degree, minus 45 degrees, more or less, or minus 40 or so. And then spiral down into the center. So you have some dynamo going on in the central kiloparsec, and then you have a large scale dynamo along the few kiloparsec inner bar that go into the spiral arms afterwards. So at least the papers by Ranier, Beck and company, they have some radio parametric conservation of bars, and they have seen a very strong order magnetic field in the inner bars.
Thanks a lot. And at the end, maybe when all the questions are done, we can discuss more. Thank you.
Yeah, no problem.
Okay, I think Carolina was...
Okay, thanks. Can you hear me?
Yes.
Okay, I also want to thank you for the very nice presentation and for these beautiful images that you are showing us. So concerning Centaurus A, for example, you showed us at the beginning this also nice video with this 3D geometric representation of this kind of warped disk.
Mm-hmm. Mm-hmm.
I didn't get very well how this fits into your data and the polarization that structure that you have. I was thinking, for example, is it possible that this lower polarization area that you have, that you associated to turbulence, are due to kind of are the region where you have more of these wrap, and there you have kind of different contribution from magnetic field aligned in different way that cancel out each other.
Yeah. So yeah, that's a very good question. So here I show the far infrared observation that we have. So as I say, the contours here on the left, the color scale show the total intensity, and on the right, the color scale show the polarized flux. So these graphs that you mentioned are these graphs here on the upper part and in the lower part, and those are actually highly polarized. This is pretty interesting. So and also they're the ones that are closer to our LIO side too. So this part on the bottom is on the other side, and this one on the top on the on this east side of the warp disk are on the back side. Along the LIO side of this back part, yes, maybe a contribution of the column density along the LIO side on the outer part, but in the inner edge of the warp, they're very highly polarized, and they're more or less ordered or following the magnetic field. They're not ordered a long distance because you have some dispersion, but you see that they are highly polarized up to 8 to 10% polarization. So you have magnetically aligned dust grains following this warp disk in this case. So the contribution of extinction or yeah, basically extinction is very low in the case of the warp regions of the galaxy, of the warp disk.
Okay, thanks.
Yeah, okay.
I think Nick had his hand up, but I think he left. So Rafael, I think you're next.
Thank you very much for the presentation. It was very interesting. I would like to ask some. Can you observe with all of the bands simultaneously?
No, simultaneously. We need to so every band is independent to each other. You need to do so let me see here we have 5 bands, and you need to observe in each one of them independently.
Okay. And if I may, second question, how did you estimate the magnetic energy density as a function of the radius, if I remember correctly?
I
mean, technically, what you use this method, the Chandrasekhar method, and then, but did you do it in a scale-dependent way, so you can measure it outside the center of the galaxy?
Yes, for M82, so what we did was we used this modified version of the Chandrasekhar Fermi method to add the contribution of the large scale flow. So this magnetic field strength is the average of here of this. So what I show here is the observation of Hawk Plus, and you see the observations. So the magnetic field lines in the center, and we use the velocity kinematics of the CO in order to separate the structures of the velocity along the starburst and the outflow, and we distinguish 4 different areas. One is like was dominated by these vertical vertical velocities. In the center, you have another component along the disk, and then you have 2 more components in the outflows. So we end up in a situation that we have one single component that is dominating, and we call it this starburst mask. and it's more or less the same field of view as the one that we have with Hawk. So within this mask, we estimate the mean magnetic field because we have the contribution of, we know how much is the column density, we know how much is velocity dispersion, and we know how much is the dispersion of polarization angles. We can estimate the mean of the magnetic field in this mask, but because we have a map of a pixel by pixel base of the column density, velocity dispersion, and also the position angle, we can actually make a 2D map here, a 2D map of the magnetic of the turbomagnetic field energy. So this map is using, so it was performed using the beta plasma definition, where you had the ratio of the kinetic plus hydrostatic energy divided by the magnetic energy.
Mm-hmm.
And you have 2D maps of the velocity. You have a 2D map of the surface brightness, and you also have a 2D map of the magnetic field. Well, no, you don't have. So you have the medium, the average of the magnetic field in the mask. So you can actually estimate pixel by pixel mask, forcing the map to have the medium beta plasma within the mask.
Sorry. Then, how did you estimate the plasma beta?
Yes.
Do you have an independent way?
Yes. So let me show you. Let me see if I can show you this. Okay. So here is so let me see all the details. So here what I show is the magnetic field. So the DCF method depends on, so on the velocity dispersion, the column density, and the dispersion of the position angles. And then we have all these two maps here. So you have the column density from Johnson et al. You have the velocity dispersion, and then you have the velocity orientation. So, and then after that, what you do is to estimate this beta plasma. So, and then what you do with the beta plasma, you can estimate it within the mask, which is like this 0.5 value. And then you make use of the definition of the kinetic energy, electrostatic energy, and magnetic energy, which is a pixel per pixel base. And you make this beta plasma to be, you make the map to have a beta plasma within the Starburst mask. So yeah, I don't know if I'm explaining that. Or I don't know if you have been getting this. So the independent.
Okay, I understand the previous things, but I'm still confused about how the plasma beta is estimated, because from what you said, I understood that you use the plasma beta to construct the magnetic field map.
Yes. So the beta plasma is the medium beta plasma within the Starburst mask. Which is being estimated using the UV, is estimating the median of the magnetic field in the mask, the median of the kinetic energy in the mask, and the median of the hydrostatic energy in the mask.
So first of all, you have to compute the magnetic field energy, the magnetic field, then the magnetic energy, and then the plasma beta.
Exactly. And
this understand. I thought that you were computing the plasma beta with an independent way.
No, exactly. Yes.
Oh, okay.
Yes, I use the measurement of the magnetic field through the modified DCF method to estimate the beta plasma.
Okay.
Yes.
Okay.
Yes.
Thanks. Thanks a lot.
Yeah.
Okay. I think we are at the time, but I don't know if anyone else has any other quick question they want to ask. Okay, otherwise, yes, we can thank you again, Enrique, for this nice presentation. A lot of interesting results